Good morning, everyone. Thank you to the session chairs and everyone for joining this session. My name is Ibn Kausar, and today I'll be presenting the paper titled Transfer Learning of Tabular Data by Fine-Tuning Large Language Models. Before we talk about today's topic, let's see what are the data domains that we use in deep learning. We see image data, we see speech data, text data, video, and graph. Even though we have a wide range of data domains in this deep learning literature, in AI, data and images are often used interchangeably. Moreover, we also have one more domain of data, that is heterogeneous tabular data sets. And in tabular data that are structured in rows and columns with a heterogeneous feature space. Tabular data can come in spreadsheets, relational databases from engineering, health science, commerce, and banking sectors. Let's see more into this, how tabular data are different than other data types. Here is an example of image versus tabular data, where we can see that in the sample size perspective, tabular data sample size are very small, almost 10 times smaller than image domain data. And also in tabular data domain, we do not have any transfer learning method, whereas for image and data, we have a standard transfer learning proposed method. And also the deep learning literature shows that tabular data is the last unconquered castle for tabular data and deep learning methods. And also deep learning is not all you need. And Greenstone says that tree-based models outperforms neural networks on tabular data. Even though we can see in tabular and for image model, we have a large pretend image model named as ResNet. We have a large pretend text model as large language model based methods like ChatGPT and other LLMs. However, for tabular data, we do not see any pre-trained model, and it is not possible to perform transfer learning. Therefore, as the LLMs are becoming ubiquitous and versatile source of knowledge, the question arises that can we leverage LLMs for tabular data? Let's say if we convert the tabular data into this structure here's an example of tabular data with numerical, text, and categorical features. And if we convert this into a textual representation with some instructions, specific instructions, can we pass it to a large language-based model like ChatGPT or Llama to perform the long-awaited transfer knowledge of tabular data so that we can do feature representation for classification. Here are some work has been done in this direction. However, it is on in-context learning mostly focused on, where it shows in-context learning is basically prompting a set of instructions to large language model with the data and instructions and to get the output. However, these in context-based learnings based methods are restricted to a specific token size. Therefore, it is limited to zero or few shot learning. And it relies solely on prompt engineering. We cannot do any transfer learning using this in context learning. Even though there has been some work in transfer learning, which is basically fine-tuning of an LLM. However, this fine-tuning of transfer learning, one of the work that tries to perform transfer learning of LLM, this work only focuses on using the large language model as is to transfer the knowledge without changing the architecture for tabular data specific. And another work that is only limited to future learning for transfer learning. Even though these are the limitations, we can see one advantage of transfer learning, which is that we can work with limited number of samples to transfer the knowledge of LLMs to tabular data. Therefore, we hypothesize that knowledge transfer using large language-based models can enable tabular text cross-modal transfer learning. Here is an example how we do it. So let's say this is the data set. This is a data set with 4 different features and the labels. which is the tabular data, we can convert each samples into sentences and multiple sentences to convert it into sequence of sentence. And we can use the metadata with the data set, like the task description. What is the task that we are trying to solve, with some feature descriptions and with some specific instructions? If we combine this sequence of sentences and this metadata, we can do that with a specific prompt template. And this whole process is called as data serialization. Once this data is serialized, we can pass it to a tokenizer. And this tokenizer, will talk in detail about how this tokenizer works. But this tokenizer gives us the token IDs. And from these token IDs, we pass it to a token encoder, which gives us the corresponding token embeddings, which are passed to a GPT model. For our experiment, we use GPT 3.5 from OpenAI. And this GPT model gives us the text output. So please note that for this experiment, we only use GPT model. We do not train or update any model parameter. So this is only on forward pass. Once we get the text output from the GPT model, we encode it back to tabular data and pass it to a standalone classifier model to train or to learn the output tabular data that we got from the GPT model. Before we dive into the experimental detail of the tokenizer and token encoding process, let's see how we need to design the prompt. Here is an example. So first, we need to provide basic information and the example of the samples with the task description, feature description, and serialized examples. Next, we need to give more instruction about how we want the GPT model to do the reasoning. With, let's say, in step one, we want to analyze the causal relationship. In step two, we want to give some examples to infer different conditions. And third, we also want the GPT to respond back to us with a specific format where we specify the format in the response instruction. Once we have all this, we pass it to a GPT model. So let's see an example of how the data are input to GPT model and how we convert everything to pass it to a classifier model. Let's say this is an example where our task is, does this patient have diabetes? Yes or no? We provide the metadata of each feature, and here are some examples with the corresponding answers. Once we pass all this, once we have all this ready, we also provide what are the format of the response we want. And this is how the GPT model respond to us. We have the conditions for class no, and we have the condition for class yes. For simplicity, we only show three different conditions here. Once we have all these conditions, we encode this back to tabular data. But in this stage, we have two different substeps. One is we extract the rules from these conditions and we convert it to binary features like this. And once we have this binary feature generation done, we consider each of these as one rule, and we have all the rules. Once it is ready, we pass it to a standalone classifier model to train these rules based on these rules. This is how we perform in-context learning for tabular data. Following this is our proposed end-to-end LLM fine-tuning method, where we take the same tabular data and convert each sample into sequence of sentences and pass it to a tokenizer. And the tokenizer converts each words into specific token IDs. And this is, let's say an example text is how are glacier caves formed. And if we pass it to a tokenizer, it first tokenizes into simplest form of words and then gets the corresponding token IDs. And once we have the token IDs, we pass it to a token encoder. This token encoder gives us the corresponding token embeddings. These token embeddings are then fed to the GPT model, which is pre-trained on language model. We transfer the knowledge of the language model by fine-tuning based on these token embeddings that we got from the tabular data. And once we get the corresponding embedding output from the distill GPT-2, we pass it to a classifier head, which is also part of this training, so that this classifier head can back propagate based on the prediction of the distill GPT model and the actual ground truths. By doing this backpropagation, we optimize the distill GPT to learn the embeddings of the tabular data to perform the transfer and knowledge from text model to tabular model. For this experiment, we have used 10 different datasets. 5 datasets are from the UCI machine learning repository, and 4 datasets are from OpenML data repository, and 1 real-world data medical dataset from Mimic3 database. And we compare our base method with few baselines. One is GBD, which is considered as the best on tabular data. And we consider also with MLP layer with 3 fully connected hidden layers, 128, 64, and 32 neurons. And we also compare with the state-of-the-art deep tabular data learning paper known as SCARF. And we also compare with the FEED LLM, which is considered as the state-of-the-art in-context learning of tabular data. Following to that, we fine tune. We have proposed 2 fine tuning methods. One is LLM model without fine tuning, where we keep the model what's frozen, and we perform LLM model with end-to-end fine tuning. Here is the result of this method, where we show the average area under the curve scores for 5 cross-validation faults. One is, this is the GPT results, and these are the MLP results for 10 datasets. These are the deep learning based method SCARF result, and these are the LLM models result. Among all these results, we can see that our proposed transfer learning with LLM is on par with the best gradient boosting trees on one dataset, which is the diabetes dataset. And it beats deep learning based solutions on 6 datasets. And it also beats LLM model, feed LLM on 7 datasets. Overall, we can say that our proposed end-to-end fine-tuning method is best among all deep learning-based solutions. We can also see the time complexity of each of these methods to get a better understanding which is more robust among the deep learning-based methods. Here we can see that feed LLM takes long execution times due to the API latency, and transfer learning is end-to-end transfer learning is over 2.5 times faster than feed LLM and 4.7 times faster than SCARF model. Therefore, we can say that proposed transfer learning offers a good trade-off between efficiency and accuracy. To summarize, transfer learning of LLMs are superior to in-context learning and deep learning for tabular data, and cross-modal transfer learning is effective because of big performance contrast between frozen and fine-tuned LLM widths. Token size limits hinder in-context learning and prompt engineering. LLM transfer learning faster than deep learning-based solutions for tabular data. To conclude, LLM fine-tuning shows promise for text-to-tabular cross-modal transfer learning in domains with limited samples where large pre-trained models are infeasible. Transfer learning with LLMs poised to surpass state-of-the-art methods of tabular data. In future, we aim to develop tabular-specific LLMs to outperform models like gradient boosting trees. We can scale up the training to larger databases and multimodal tasks. We can also validate to real-world applications like engineering, healthcare, finance, and beyond. For this presentation, I have used these references. If you have any question, I'll take them now. Thank you.